The Pythagorean theorem is one of the most well-known mathematical formulas in the world, relating the lengths of three sides of a right triangle. We are taught it in school and use it for all sorts of homework questions, but have you ever stopped and wondered why this beautiful formula actually works? Let's take a closer look. One of the earliest known proofs of the Pythagorean theorem, and perhaps the most famous, occurs in Euclid's Elements, written by the great mathematician Euclid around 300 BC. The Elements are the most well-preserved ancient manuscript, aside from the Bible. The Elements are known for their rigor and emphasis on proof, which is different from the prior societies who only cared that the results worked. They didn't care about why. Let's dive into his proof. Remember, the goal is to prove that this side length squared plus this side length squared equals the hypotenuse squared. So, this square's area plus this square's area must have the same area as this square. The first thing Euclid did to start his proof was draw a line starting in the right angle of the triangle we're interested in and perpendicular to the hypotenuse and extend it all the way down to the bottom of the square. So, the next thing he did was to draw a line from D on my triangle all the way up to A to form a new triangle here. And he also drew a line from F all the way to C on my triangle to make a new triangle here. Well, first of all, this side and this side are both on a square, which means they must be equal. Similarly down here, this bottom one's also a square, so this length must be equal to this length. The last thing we want to look at is this included angle FBC on one triangle, ABD on the other triangle. FBC has the right angle from a square plus this other angle ABC. Angle ABD has a right angle from a square plus the same angle ABC. So, by side angle side, we know that these two triangles are congruent. So the next thing we want to look at is the area of both of those triangles. First, look at triangle ABD. We can say that its base lies on side length BD, and its height is BH. So the area equals 1/2 times the base BD times the height BH. Next, let's look at rectangle BDKH. Well, that rectangle we can say has base BD and height BH. So the area is simply BD times BH. So the area of rectangle BDKH is also just 2 times the area of triangle ABD. Well, what about the other triangle? FBC has a base on FB and a height of AB. It's hard to see, but the triangle does come all the way out here and is parallel with A right there with the base. So we can say the height is AB. So FBC equals 1/2 times length FB times AB. But we also know AB and FB are sides of a square, so they're just the same. So we could just say times FB squared. Well, last thing is this square over here, ABFG, is just FB squared. So that means ABFG, we can also write that as 2 times triangle FBC. But we said triangle FBC and triangle ABD we're congruent. That means the area of square ABFG equals the area of this rectangle here, BDKH. And you can see how this leads to the complete proof. If we were to do the same process, drawing in triangles on this side, we could see that this right rectangle has the same area as this upper square. So, by construction, we have the area of this entire lower square equals the area of the square of this leg plus the area of the square of this leg. Another clever proof of the Pythagorean theorem, which I think is the easiest for people who are new to it, is by constructing two squares where side length is a plus b. As you can see in the first one, we have the area c squared shown, and it is the area of the entire thing, a plus b squared, minus 4 of these triangles, which have area 1/2 AB. This bottom one would have a squared and b squared showing, and their area is also the area of the whole thing, a plus b squared, minus 4 of the same triangles, 4 times 1/2 times AB. So this is c squared, this is a squared plus d squared. So you can also see this way that the theorem holds. A third proof of the Pythagorean theorem is by using similar triangles. We would like to look at the whole triangle, the one we're interested in, ABC, and the smaller triangle, ACD. Well, both triangles have angle A in them. They also both have a right angle. So that's enough to say that triangle ABC is similar to triangle ADC. Using the same reasoning, we could say that this third triangle, CBD, is also similar to the other two. What this tells us is that the side lengths of the three triangles will be proportional. So, we can get the following proportions from this. The ratio from side length BC to AB is going to be the same ratio as side length BD to BC. And we also have the ratio side length AC to AB equals the ratio side length AD to AC. Well, we can cross multiply these to help us get to our solution. So over here we have BC squared equals AB times BD. And over here we have AC squared equals AB times AD. Well, if we simply add these two together, AC squared plus BC squared equals AB times BD plus AD. You can factor it out like that, but BD plus AD is just AB. So we have AC squared plus BC squared equals AB. Despite Euclid's strong mathematical knowledge, he actually used a low amount of mathematical facts to reach his proof of the Pythagorean theorem. We can see this pattern throughout the elements, where he tries to be as concise as possible when proving results. Please like and subscribe so you can catch the next episode, where we will dive into another famous ancient Greek mathematician.